First of all, I'd like to thank Austin because I was supposed to be giving today's seminar and I wasn't prepared and Austin just jumped in. So thank you, Austin, for jumping in to give the seminar today. Appreciate it.
No problem.
Go right ahead.
All right. Hi, everybody. Thanks for coming. So I think last week was SEM, right?
Yes.
All right. This week we're going to go very, very, very much to the other end of the how complicated a microscope you're using, and we're going to do some really fun and nifty techniques that we can do in ultra high vacuum, which is a whole different world. So we're talking great big steel vacuum chambers, long pump down times. But it's a lot of fun, and we can see cool things. The first one we're going to talk about is something that's actually new to CNS last year or so. So we got a new tool, a new toy. This thing's cool. This is called a LEAM, which stands for a low energy electron microscope. And as mentioned, yeah, there you go. It's a great big steel vacuum chamber with all sorts of bits and pipes and so on hanging off it. So what this thing is, it's an electron microscope for looking at really small stuff, but it's for looking at surfaces. This is a 2D sample kind of microscope. It is a surface sensitive tool only, and it is not the most relaxing day you're ever going to have on a microscope. It's got 6 manual aperture sets. You are manually adjusting lens voltages. Nothing is automated. It's old school microscopy. It's a lot of fun. Cool. And it works great for 2D materials. If you do graphene or molybdenum or any of that kind of work, this is totally the tool for you. It is ultra high vacuum. I mentioned that right at the beginning. What is ultra high vacuum? That means that we are at really low pressures. Everything's got to be absolutely stinking clean. So 10 to minus 9, 10 to minus 10 torque, if you're familiar with the Torr scale. And getting down there involves all sorts of pumps and heating and cooling and cleaning and so on. But if we want to put up with that, we can do a lot of cool stuff. This is a microscope that we can watch things happening in real time. We can heat materials to very, very high temperatures, well above 2500 K. So, 2200 C. And in theory, it can go hotter than that. I haven't bothered because you go hotter than that, and the only thing that's left is tungsten. So, okay. And it can go cold. It has very high resolution by the standards of this kind of tool, which means 2 nanometers. By the standards of like a TEM, that's terrible. By the standards of an SEM, it's okay. But for LEAM, this is a really good LEAM. And it can do just so many different things. This is not just one microscope. This is a bunch of microscopes all in one package, and all these wonderful acronyms, and we'll talk about what they are as we run by. It's also customizable, got ports all over it. So if you've got some wacky experiment you'd like to do in a microscope like this, we'll probably say no, but we might not. You never know. Come ask. All right. And for people who care about this, anyone who's growing anything in UHV already, we do have transfer shuttles. So if you've got an MBE or something and you're already making new samples under vacuum, you want to keep them that way, no problem. We can carry them over to this thing and keep them under vacuum the whole way. So what does this thing do? All right, here's what it does. There are 2 major types of picture you can take with this. One is called a lean picture and one is called a clean picture. Lean stands for low energy electron microscopy, and the way it works is we shoot electrons at your sample and they reflect back off and we take a picture. Easy enough. It's like a reflected light microscope, only with electrons. However, these electrons are coherent, which means they also diffract if your sample is crystal, which means that we can get diffraction images, we can get diffraction patterns, we can learn stuff about crystallography of the outer atomic monolayer of your sample, which is really hard to do any other way. And the electrons may come in at fairly high energies, so 15 kilovolts. Again, if you saw last week's SEM lecture, you're familiar with the idea that we talk about energies in terms of voltage. But they don't actually hit the sample at that energy. They hit the sample at an energy of 0 or 100 millivolts. And the way that happens is the electron beam is coming in at 15 kilovolts. Sample is also at 15 kilovolts. So as the electrons approach the sample, they slow way down and just barely tickle the surface, and then head right back out again up through the same lens. And that's a lean picture. Beam, the other major imaging mode, is photoelectron emission microscopy, and we don't even bother shooting electrons at the sample. We just shine light on it. Because it turns out that if you shine light on pieces of material, they emit electrons, which is very handy. And there was some guy 100 years ago who wrote a paper about it in the studio.
Didn't you win a Nobel Prize for it?
Yeah, I think a bunch of people. Yeah. Anyway, whatever. Yeah. So photo emission. So the shine light has to be high energy light, meaning blue, purple, ultraviolet, that kind of thing. But then electrons get extracted out of the sample and They go right up through the same imaging column that we use for lean, and you can take pictures with them, which is neat. Or you can send them through an energy filter and make nifty spectroscopic measurements of their energies, and that tells you things about your sample. And I'm going to go into more detail. You know what? Let's just move along. Not to worry about it. So I did some little animations to try to explain what text is going on. What?
Close the box that popped up.
Thank you. Close off. All right, cool. So how to think about lean. Here is a simple thing you might try to measure in a lean. Here's a piece of silicon carbide, and it's got a couple sheets of graphene on it. And we all know graphene, right? It's like graphite, it's one little layer of graphite. All right, so let's say we've got two sheets of it on there, and we want to look at it. And we've got a 15 kilovolt electron coming rocketing out of the sky, and we got 15 kilovolts on our piece of silicon carbide. What happens? Bounce. That happens. We're back. Here we go. Bounce. It bounces because they're exactly the same energy, 15 kilovolts in both cases. The electron doesn't even really touch the sample. It slows down before it even hits it. But okay, it interacts with it somehow. The edge of the electron's wave function touches the sample, and so we get some sort of texture in our picture, and it looks like this. It's kind of a mess, but okay, there's some sort of picture, right? But what if we were to turn down the voltage on the sample a little bit? Just 2 volts less on the sample. Now, the electron's not going to slow down quite as far away. It's going to go a little deeper, and we're going to start to get some actual contrast. And in fact, if we keep doing this, if we keep turning down the landing energies, or sorry, the sample energies, turning up the landing energies, we probe deeper and deeper into the sample, and we start to interact with deeper and deeper parts of this material stack. And so a lean image is not really what we collect. What we collect is a stack of lean images taken at different landing energies, and then we go interpret them. And that is not simple at all. But okay, we're not going to worry about that. The idea is by changing how much energy the electron effectively lands with, we change how deep into your sample we probe. We also change the actual physics of interaction that's going on in the sample. Sounds weird. What can we see? Okay, here's some stuff we can see. Here is some graphene actually being grown in real time. You can see nice hexagon facets on it. That's a little triangle graphene. It's nucleated at a point defect on a piece of silicon carbide. This particular sample got really hot because, as I mentioned, we can make things really hot in this tool, and it started to spontaneously grow graphene. And you can see this single monolayer of graphene, but you can not only see it, you can see all the little point defects in it where it hasn't grown beautifully. They show up as contrast as well. You can also take a diffraction pattern off it. Here is the diffraction pattern of graphene growing on silicon carbide. And again, this is a diffraction pattern from a single monolayer of atoms, which, if you know the physics of diffraction, is kind of head-scratchery, but it works. Yay. Since we have a diffraction pattern, each one of these spots in the diffraction pattern, my pointer, is actually a full image. So we can take a little aperture, a piece of foil with a hole in it, put it in front of this pattern, mask off everything except for one spot, magnify it way up, and take an image of just the diffracted electrons, the ones that interacted with the crystal structure and got bent off to some funny angle because of physics. And we get these dark field images like the one on your right, where some of the graphene is light and some of it's dark because some of it's oriented one direction, some of it's oriented the other direction. And there's actually even these fun little triangular structures which happen when you have 2 sheets of graphene on top of each other with some twisted angle in between them. You get this moiré effect. Really entertaining. That's the kind of picture you can take with lean. This applies to 2D materials. It also applies to the actual surface of your material. If you want to look at things like surface reconstruction of a crystal, if you're a hardcore surface scientist, lots of other stuff you can do. It's pretty neat. But we're going to move on because we have a lot to cover. So, heating and cooling. This is an example of what happens when you get something really hot and you look at its surface. These are 2 different sets of atomic planes. Sets of atomic planes, meaning different orientations of the crystal. And this piece of silicon happens to have a crystal structure such that if you have a rough surface, you get alternating 90-degree turns in the crystal with each atomic set the surface has. And so we use a dark field mask, and we take that spot and put it over here, that spot over there, and we get these 2 images of the different planes. And that's all very nice. But what if we heat it up? And if we heat it up, we get to watch these atomic planes grow. And these are atoms actually migrating around on the surface of the silicon, trying to flatten the little hills out. You can imagine this sort of like a geographical topography plot. And since it's warm, it wants to be flat. It doesn't want to have hills and bumps. Everybody wants to have all their bonds satisfied. So everybody's just going to move around. You also notice in this particular one, we got some weird line features that stuff is bouncing off of. Those are silicides. Those are a different material. It's embedded in the surface, and the atomic planes can't grow through them, so they bounce off. You can watch this sort of thing, which you read about in your material science textbook, but you can watch it happen in real time. And obviously, you can do it in more interesting systems than just a piece of silicon, but a piece of silicon is easy. PEEM, like I said, we're moving on faster. We've got a lot to do. PEEM, photoelectron emission microscopy. Back to our same picture, but this time our electron is starting out in graphene, and we're going to shine some light on it. We're going to mercury arc lamp. It's real bright, broad spectrum lamp, so all the colors are in it. What happens? And I'm going to draw some band structure, like highly cartoony band structure off to the side for people who like it. But here's our highly cartoony electronic band structure, and there's the electron in the valence band where they live. And here comes our colorful light, and what happens? The electron absorbs it, and it goes above the work function, which is the amount of energy it takes to take an electron and just yank it the heck out of your material and throw it into space. Unless it doesn't, because if it absorbs light that's low energy, it doesn't make it out, and we don't get anything. And depending on which color of light it happens to absorb, it comes out with different amounts of energy, and that's all fine. We don't really care. Having come out of the graphene, it now notices that there's 15 kilovolts around, and zoom, off it goes. And then we take a picture with it. And the contrast we get in this picture is coming from differences in work function. In other words, depending on where your work function level is, different numbers of these are going to make it out. Now, if the work function is up here, only the purplest electrons absorb the high energy photons to make it out. This is a picture of that same graphene thing as we were looking at before. These silicon carbide's got little ribbons of graphene growing on it. We're seeing contrast between the silicon carbide and the graphene. Spatial resolution in this is not as good, but it's a totally different physical mechanism. So what do you want? So PEEM is nice because PEEM allows you to see all sorts of things and is a little less fussy about your sample than LEAN is. LEAN really does look at the top atomic monolayer and nothing else, because those incoming electrons have basically no energy when they come down. And if you've got dirt or water or oxide or something else on top of your sample because somebody put their finger on it or whatever, that's all you're going to see in the LEAN, because that's all the electrons hit. Whereas PEEM is shooting light, and light goes through lots of stuff. And as long as the electrons you excite can get back out again, you'll get them. So PEEM is sort of our large area, easier to use mode. And you can look at lots of things. These are different grains of metal in a piece of Inconel, which is a nickel alloy. And depending on the orientation of the crystal, the different facets of the crystal have different work functions. So you get these different contrasts. And you can see little pockets of oxide trying to grow on the surface of it here and here and here. This is a device made in the clean room. You can image these too in PEEM, and you can see the work function difference for the different metals and the little tiny, they show up, they do okay. The little tiny ribbons of etched graphene that someone was contacting with all these metals and so on. You can actually do one other trick. All you need to do to take a picture on this microscope is get electrons to come off your sample. Doesn't really matter how you do it. Shining light is a good way, shining electrons is a good way. You can also just heat it up. Once your sample is glowing yellow hot, it turns out it's boiling electrons out too. So if you put a piece of, in this case, aluminum nitride, and you get it up to 1100 C, yeah, it starts making electrons, sure. Why not? You take pictures of those too. I don't know of any actual practical use for this phenomenon, but it exists. It's not listed on the instrument when you buy it as an imaging mode, so I was kind of shocked because that actually works. But cool. ARPES. Anybody in here ever done ARPES before? Yeah, okay, cool. Good people. So this is not going to knock your socks off in terms of ARPES resolution, but let's not worry about it. It exists. We have it on site. You can come try it. If you like it, you can go to a synchrotron and do really, really good ARPES. What's ARPES? This is angle-resolved photoelectron spectroscopy. So starting with the same gimmick, we're going to shine light, we're going to electrons out, but we're going to go a little further than that. This time I'm going to shine real high energy light, like 20, 40 eV light. So that's pretty ultraviolet light. We need to make a plasma out of helium. It's a whole fuss, but we can do it. And we shine the light on, and it's monochromatic. We're not using broad spectrum light anymore. And what happens? Well, okay. Same picture, electrons hanging out, and up it goes, right? And that's all good. But one thing's a little different. Since we're using monochromatic light now, if we had an electron that wasn't sitting, for those who know about band structure, right in the middle of our band structure, but had some momentum, somewhere on the dispersion curve, it's going to maintain that momentum and that energy difference when we do this, and it's going to end up going to a different spot in this diagram when we promote it up. Which means that if we put something that separates out radiation by its energy, which is a prism, for electrons, that's a magnetic prism, for light, it's a glass prism, then they're going to get separated out by energy through that same way we put before. And that means we can make a little map of the energies and, as it turns out, the in-plane momenta of the electrons, which in other words means we take a picture of the valence band. That's what ARPES is. ARPES is a way of taking a picture of the valence band of your material direct, which for people who care about valence bands, it's a really big deal and it's super cool. And we have whole elaborate accelerator facility end stations that are designed to do just this, and they do it a lot better than this tool does. But this tool is here and you can use it. So here's some actual data off our tool. That's the valence band graphene. There's also a complementary technique you can do in the lean, which I'm not going to talk about, it's too complicated, which is the conduction band through a sort of similar mechanism, but coming the other way. And it is good enough ARPES that you can get Z-cuts, you know, those of you who've done it, and you can actually see the direct points and all that sort of thing. So if you want to try it out, we can try it out. We don't have to go. Sample requirements. Whenever you talk about electron microscopy, you always got to worry about your sample, because if your sample doesn't fit in the microscope or is too dirty or whatever, then you can't do anything. So you got to bring. The sample requirements in this are kind of restricted. The sample carriers are these little square jobs. They got a hole in the middle. That's because the actual surface you're going to look at is supposed to face outward through that hole. And it's not very big. Your sample cannot be any bigger than a 10 millimeter circle or an 8.1 millimeter on an inch square to fit in this thing, but it has to be bigger than 4 millimeters or it falls to the hole. So that's a little tedious. But okay, we have mounting tricks to make this work if your sample doesn't fit in those sides. If sample smaller than 4 millimeters, you've got mounting tricks. If it's bigger than 10 millimeters, I got half size. No worries, make it work. Your sample needs to be flat. It needs to be flat because if it's not flat and we put 15 kilovolts on it, you're going to get diverging field lines coming off all the bumps, and your electrons are going to get bent off to the side, and they're not going to go back up through the lens, and we're not going to get a picture. It needs to be conductive because they have to put 15 kilovolts on it. How conductive? Not that conductive, it turns out. Silicon carbide is pretty damn insulating, and that actually works fine. Throwing titanate works fine. Silicon with native oxide works pretty well. Sapphire, no. Don't bring me sapphire. That's not going to work. We have adapter plates to hold now 3 millimeter TM grids. So if you've got a sample that's already on one of those, we can give it a shot. It has to be clean. I already mentioned this, but your sample's got to be clean, and this is tough. Everything that comes out here into the world, everything you've ever touched, seen, unless you do this sort of work, has at least a monolayer of water on it. Even stuff that you think is completely dry has a monolayer of water on it, and surface tension is just that strong. And if you want to get that water back off, you got to heat it up real hot. And so under UHV conditions, we got to get that water off because we don't want to see it in lean. We got to heat up to at least 120 degrees, usually more like 300 or 400 degrees. If your sample doesn't like getting that hot, then we got to find another way to clean it. And most people's samples don't like getting that hot. It's not great for most materials to get that hot. So we have other ways of dealing with it and getting around this problem, but it's something you have to factor in if you want to do this one. So that's my quick summary of the lean and ARPES and all the other related things. It's a 2D imaging technique for looking at flat stuff and learning a whole bunch of neat electronic details about that material. And it's neat and cool. We have the only user accessible one on this continent. So if you want to try it, come on down. Let's add a dimension. How about 3D? Yeah, this is the other UHV fun toy we've got going. So we're going to completely change gears and talk about a different technique. But we'll have questions at the end. We can go back to any of these slides. So let's talk about a different technique. This one's called active probe tomography. It's a three-dimensional imaging technique, three-dimensional measurement technique. And what the heck is it? Well, actually, we got to talk about a lot of stuff to talk about what it is. So I go through a whole bunch of little things. And again, I'm sorry if I'm going a little fast and trying to mash two talks into one. So what it is a type of mass spectroscopy. And we'll talk about what that is. And it's a three-dimensional type of mass spectroscopy. It works on single atoms. In other words, this is a way of getting a data set, which is a volume of about a cubic micron, not very big, containing all, with air quotes, of the atoms that were originally in your real material, and every atom is positioned where it should be, and every atom is labeled by its element and isotope. And I'll show you some of those data sets because they're pretty cool. But to understand how we get there, we have to talk about what mass spec is, because I'm sure that hasn't been covered yet in the summer, and what tomography is, and a bunch of other terms. So let's do that. So what's mass spec? Imagine you had a bunch of atoms, different atoms, and you want to know how many of each one you've got. How do you do it? Well, one way you can do that is you can shine radiation on it, and then radiation comes back out. And then you collect the radiation that comes back out, and then physics, and you get some number of atoms, or must have been, to get that radiation. That was easy. These are the emissive spectroscopies like EDS and lots of other ones, basically, where we're exciting the atoms, and then we're getting radiation based on how many electrons they had in various orbitals or other things. As kind of an indirect way of going about it, the error bars tend to be kind of large in many of the techniques. It's not very easy to calibrate this, but okay, you can do it. But what if there was a simpler way? What if there was a brute force way? What if you just took it and blew it apart and then picked up all the bits and then counted the bits? And that's called mass spectroscopy. We take your piece of material and we explode it. Great, fun. And then we collect all the atoms and we sort them into buckets, depending on what kind of atom they are. And great, now we have an exact count of how many atoms of which sort you had, give or take. And that's another way to get to the same result. That's mass spectroscopy. That's what we're doing in the atom probe. Specifically, we're going to do a type called time of flight mass spectroscopy. So we're going to get into details. How do we do the sorting? How do we do the exploding? We start off with our chunk of material, and we zap it with something. With what? Don't worry about it right now. We'll get there. We zap it with something. And when we zap it, we have a stopwatch in our non-zapping hand, and we start the stopwatch, and the atoms go flying. We give them a push. In our case, we give them a push with an electric field. There are other ways you can do it. But anyway, you give them a push, and it's a calibrated push. A push where we know exactly how much energy we put into the system. We know how hard we accelerated these suckers. And we send them down a racetrack of known length. And as they go along, the different masses start to separate because we push them all with the same amount of force, but they weigh different amounts, and they mass different amounts. And so they start to spread out from each other. The light ones get accelerated to go to higher speed. The heavy ones don't get such a high speed. Right. And we keep looking at our stopwatch. And at a certain point, they start to arrive at the end of the racetrack. And when one arrives, we stop our stopwatch. And we build up what we call a time of flight spectrum. And we put little counts on our time of flight spectrum, depending on how many things took a certain amount of time to arrive. Conveniently, atoms don't have a continuous distribution of masses, right? They either got a proton on them or they don't. So your resolution only has to be so good in order to tell the difference between two different mass atoms. Cool, so now we've got a time of flight spectrum. That is not a mass spectrum. We want a mass spectrum. We're getting there though. What do we do next? We take the time of flight spectrum, and we take advantage of the fact that we know how long it took an individual atom to go down the racetrack. We know how long the racetrack is. So that gives us distance over time, which is velocity. And we know how much energy we gave them because we know how hard we pushed, which gives us E, which means we got everything in this equation except for M, which means we can rearrange everybody and solve for M and turn the time of flight into a mass. Actually, a mass divided by charge, because we use an electric field, and if they're double charged, they get twice the kick. But close enough. This is time of flight mass spectroscopy. And this is a handy way to separate out your atoms by different masses. It works real well. It's got its limitations, but it works real well. Cool, cool. Yeah, asterisks. So that's mass spectroscopy. That's the first half of what we're doing in atom probe. The second half is the word tomography. What the hell is that? Tomography means drawing something by slicing. Essentially, tomography is what you do when you want to look at something in more dimensions than the tool you've got is capable of actually directly resolving. If you want to take a 3D picture of something, one good way to take a 3D picture of it is to cut it in little thin slices and take a picture of each slice. And then just sort of hold them up and kind of look at them from the side and things and imagine 3D. That would be tomography. You start with something and we slice it. Unfortunately, whatever we're slicing it with tends to destroy part of the object. So there are portions of it that we do get data from and portions we don't. And so we end up with this data set that looks like that. Pretty typical. It's always missing volume. Well, okay, that we can sort of figure out what we're looking at from that. If you look at that with your eyes, you can imagine that there's a circle there and a smiley face, right? But that's because we're used to looking at circles and smiley faces, and our brain is filling in the missing parts for us, which is the process we call reconstruction, which you have to do. Now, one simple way to do that is just to say that the missing volume that we didn't capture has to look pretty much just like the stuff on either side of it. We call that interpolation. We just draw straight lines between everything, and we end up with something that's kind of right and doesn't involve any really egregious assumptions, and we can put error bars on it pretty well. Of course, we can add as many assumptions as we're comfortable with, and if our assumptions are really good, then we get something back that looks very much like the original starting object. And if our assumptions aren't so good, then we get some artifacts. Yeah, and that happens a lot. And then the question is how to do this right, and how to tell you did it right. And we're not going to worry about how to do that, because it's a whole discipline to figure out how to do that. Soon that we know how. What do we get for all this trouble? This is what we get. We get these data sets. So in these data sets, the dots are all atoms. The surfaces are surfaces we drew to indicate that everything inside the surface has more than a certain percentage of atoms. But there you go. Every one of those little rotating gray dots is a silicon atom. The blue is cobalt. And we really are counting the suckers. And they're all where they ought to be. We got the same sort of thing going over here for a ceramic with tantalum and zirconium. We got a 3,5 with indium aluminum arsenide and germanium down there. This is fully 3D atom imaging. Now, we destroyed these pieces of material. We blew them up, but we know where all the atoms were. So we learned something. And we can do all sorts of complicated 3D analyses on these, do composition measurements in 3 dimensions and stuff that you just can't do any other place. That's cool. How do we do it? This is what the inside of this tool looks like. We take your piece of material and we make a little pencil tip out of it, sharpen it. And you can do this a bunch of different ways. We use a tool called a FIB, focused ion beam. There's going to be a whole lecture on that later this summer. They're very, very cool use of tools. Just accept for the moment that we can do that. We make a little sharp tip, and by sharp, I mean really sharp. I mean, we sharpen your piece of material up until the point is like 10 nanometers, like 100 atoms across. Cool. Why would we bother with that? Well, we then stick it under an electrode, little cone-shaped electrode. Here's what the samples actually look like, by the way, by the time we get done with them. Little pointy needles, as imaged by SEM. We put it under a hollow cone-shaped electrode. They look like this. We cool it way down. This sample's at like 20 Kelvin. Why has it got to be so cold? It's got to be so cold because heat means things are moving. Heat means that the atoms in your piece of material are buzzing around. And we want to actually get a measurement of where the atom's supposed to be sitting. And if they're all buzzing around, they don't have a very meaningful center position. Our resolution spatially goes down. So we cool it so they all stop buzzing around, hold still, and get a damn look at them. And we put it under ultra-high vacuum again. So everything's got to be clean, it's got to be dry, all the same practically applies. All right. And then way up behind the hole in our electrode, we got a fancy detector called a microchannel plate, which is basically you take the capacitor and drill a bunch of holes in it. Please don't do that. Why? Well, the way this thing works, remember, we're doing time-of-flight mass spectroscopy. You've got to blow your sample apart. We got to rip atoms right out of it. And we do that with really big electric fields. We want to get fields on the order of several volts per angstrom, which is an absurd electric field. That is stronger than the fields that are actually present between 2 bonded atoms, which is, of course, the point. The whole point here is we want to overwhelm the bonds keeping your material in one piece and rip it apart. You cannot produce fields like that on a bulk object. Way before you get to that kind of field on something you can hold in your hand, your power supply will have caught on fire, all the wires will have melted, and you'll have ozone everywhere, and it's going to be awful. But you can do it with a very small object, especially a pointy object, because as we remember from E&M, if you have a pointy thing and you put voltage on it, you get field lines clustered at the pointy end, and you get very large field magnitudes for comparatively small voltages. In this case, a few thousand volts is enough. So we put a few thousand volts on your pointy little tip with a counter electrode nearby, and we turn it up until your tip almost comes to pieces. We don't want it to just all explode at once, though, because remember, one of the important things about time of flight is we got to have that stopwatch, which means we got to tell it when to explode. So we hang out just below the field at which your sample explodes. This is a very exciting sort of measurement. And when it goes wrong, so does your sample. And then we give it little kicks. And we can kick it with a voltage pulsar and just kick it up over that field threshold, and atoms fall off. And that works pretty well. They come off as ions, they get accelerated away, they go up through the electrode and hit our detector. We know the distance between the two. We know the amount of voltage we applied, which means we know the energy. We have our stopwatch, so we know the time. Fabulous. We got time of flight mass spec, and our detector is a position sensitive detector. So depending on where they land, we can trace them back by simulating their trajectories and work out where they started, and that gives us their spatial resolution. Cool. And then we just sit there and accumulate atoms. And this works great as long as your sample's a metal, a pure metal, like a piece of aluminum or something. But if you actually want to work on an interesting material, this doesn't work so well because that voltage pulsar is not very effective for things that are not a piece of aluminum. So for anybody's real sample, we're going to use a laser because we love lasers. They're great. We're going to use a pulsed laser, which means a laser that shoots extremely short time duration pulses of light, a few picoseconds. We shine that on, we start our stopwatch. The tip gets hot, very briefly hot. Not a lot of energy we're dumping into this, a few picojoules, that's all it takes. Man, here we're doing joules. Said we wouldn't do joules. Whatever, we're doing joules. A few picojoules, that's all it takes. Atoms come off, they land, we stop the watch. There we go. We got our time of flight mass spec, and we got our positions. And this works great. The sample prep's a little fiddly, making it works a little fiddly, but it works great. So you start out with your sharpened piece of material, and you end up with a blunt piece of material and a lot of data. And each data point is the position an atom landed and the amount of time it took to get there and the voltage that was being applied at the time. And you put them all together and you get a mass spectrum. Here we go. Here's a mass spectrum. And the resolution is good enough that you can see the different isotopes of silicon. The difference between that peak and that peak is 1 neutron. So that's pretty good mass resolution. Yeah, it's not high enough to tell the difference between a proton and a neutron, which means there are some elements and some isotopes you can't separate, like iron 54 and chrome 54, which differ in mass by the mass of an electron, which is too small. We can't measure that. But almost everything else can be measured. And conveniently, this technique does not discriminate what kind of atom you're using, by which I mean it doesn't care what kind of atom you're using. This works for hydrogen, this works for uranium, this works for everybody in between. Anything at all, lithium, all those things that are really, really hard to get measurements of, beryllium, whatever, they all are grist to our mill, we can measure anywhere. Fabulous. And then we put them in 3D, and we have this nice spinning map of where they all work. Cool. It works on 2D materials, but I don't know why you would bother. You're only going to get a tiny amount. So, materials this works really well for. Solids, don't bring me any gases. Things that don't mind being in UHV, which means they got to be vacuum stable, they got to tolerate various parts of the step. Materials for which you're looking for absolute composition measurements, everything but oxides and 3,5s. We're not going to get absolute measurements on those for reasons. But if you want relative composition measurements, meaning you think there's a difference between point A and point B, yes, those we can do even in oxides and 3,5s. Materials that are homogeneous, because the actual volume we're measuring is pretty small, cubic micron, thereabouts. So if you're looking at a material where this cubic micron and that cubic micron are wildly different, you're going to have to do a lot of atom probe to get a meaningful, statistically powerful data set that you can actually work with. I don't recommend doing that. If it's heterogeneous, it helps to already know which area you want to measure and be able to point me to it, because we don't want to just be stabbing at random. And ideally, you don't want to only have one of these things that you want to measure in the whole universe, because as mentioned, we are going to be destroying it. It's going to cease to exist. So this is the last thing that will ever happen to it. Materials that don't work. Porous materials. This is not like porous materials. There are a few materials with pores you can make work, but I don't recommend setting out to do that. Materials that don't like getting cold. If you've got a material that changes shape drastically as it cools down, then that pointy little needle we made at room temperature is not going to be a pointy little needle anymore by the time it hits 20 Kelvin. It's going to be some wonky shape. Absolute, I've mentioned absolute stoichiometry of oxides and 3,5s, not so great. Highly heterogeneous materials. Materials for which what you care about is seeing atoms that are present at levels of sort of less than a part per million. Why is that a problem? Because we do see more or less all the atoms. That's a problem because of time. To collect 1 million atoms, which is a small data set, takes you about 20 minutes. If you want to get good statistics on something that's present at 1 part per million, you need to collect 10 or 100 million atoms, which means you're looking at a many-hour run. If you want to collect good statistics on something that's at parts per billion, you're going to be running for weeks. And you're going to achieve, you're going to make the data sets be many terabytes. The computer's going to choke and die during reconstruction, and you're going to be unhappy. So I don't recommend it for that. And no hydrated samples, please. What a mess. Yeah. So let's do some examples of what you might want to do with this. Why not? Geologists happen to like this technique an awful lot. They're comfortable with mass spec. They already know a lot about the materials. Here's a material they wanted to know about. This is a very common mineral called olivine, which has a variant called clinopyroxene. Don't ask me what that means because I'm not a geologist. But these are minerals that are important in the mantle, in the solid but very, very hot material under the Earth's crust. And they have all sorts of effects on plate tectonics and what kind of rocks come up to the surface and so on. These particular geologists wanted to know what happens when this stuff gets hot and is under pressure and gets to form. They wanted to know what happens in terms of the composition of the grain boundaries. So these rocks are hot. They're like 3,500 degrees. They would be molten if they were not under the surface under enormous pressure. And so everything's diffusing around, all sorts of chemistries happen. So they wanted to look at these grain boundaries. So we put it in SEM, actually in a FIB, which is an SEM with cutting and lifting ability. And we find a particular grain boundary they want, and we pull it out. Cool. And we put it in our atom probe needle. Here are these little sharp needles. This is sort of progressive sharpening of one of these needles. They start out fat, they end up real skinny. And we have tricks to make sure that the thing we want to hit ends up in them. And then we tear them apart, and there you go, grain boundaries, which means the boundary between two different oriented crisp grains. And for some of these, which are boundaries between olivine itself, some elements segregate to the grain boundary. And for others, you get very, very, very sharp difference in some elements, but you still get segregation in others. And all this is really important if you're a petrologist, which is a geologist specializing in the chemistry and mechanics of rocks, which these guys were. And you can do all sorts of very, very careful and thorough analyses on these, doing things like chemical widths of the grain boundaries and so on, and it's all very nice. How about another thing you might want to do? Say you had a material that's supposed to emit light. Well, we got lots of those, right? I mean, you've got one up there. You see this because we got those. They work great. This particular one is aluminum indium phosphide. And it's supposed to emit light at one particular wavelength. Over here. 2.1 eV light. But instead it's emitting it down here at 1.8. So it's reddish yellow instead of greenish blue. Plain. Why did that happen? Well, this particular material emits different colors of light depending on its composition. But when they grew this particular piece of material, they targeted a very specific ratio of aluminum to indium, and they tried growing it at different temperatures, and it came out weird. It emitted the wrong color of light. It emitted colors of light corresponding to a composition that was very far away from the one that they'd originally targeted. And there was some question about why. The other problem was, you go and look at it in a TEM, which would be the usual way you would look at this sort of material and see if there was some structural problem, like it wasn't crystalline or whatever. And okay, there's some odd, rough, mottled texture in there. But if you kick in the kind of TEM you would normally use to see big composition differences, you don't really. Certainly not anything comparable to the very large difference in composition that the light emitted by this stuff would suggest. Why not? And let's talk about that. So we do atom probe. Here we go. Here's a slice through atom probe data set just showing you aluminum, and you can see right away there's some substantial difference in the amount of aluminum from one spot to another. Actually, quite a lot, like a big difference in the amount of aluminum between, like, here and there. These are all aluminum atoms drawn in purple. Why couldn't we see that in the TEM? The reason we couldn't see it in the TEM is that a TEM sample is a brick of material. It's about 70 nanometers thick, and you shine electrons through from one side to the other. And if you do that on something that has inhomogeneities on this sort of length scale, the few nanometer length scale, they all wash out. They all overlay with one another, and you don't really get anything. It's an averaged out result. But this is atom probe, and we can make slices of this data set however small we want, because it's volumetric data set. So if we were to take a teeny little slice and look at the actual fluctuation of these compositions, hey, it turns out it matches up real nice with the optical data. In fact, we can even plot it in 2 dimensions and see sort of, again, a little topographic plot of the ratio between aluminum and indium, and we can see that we got composition fluctuations over like a 5 nanometer length scale. and their fluctuations of 25% in composition, which is a ridiculously big difference. That was all very interesting and fun, and not what these folks wanted to see, but hey, yeah, found out what their problem was. Okay, so that's sort of composition of a bulk piece of material. How about interfaces? Everyone likes interfaces, right? Yeah. Here's a different theoretical light emitting object called a quantum cascade laser. These get made at CNS, they get made other places, they're really neat. It's basically electrons in, laser light out on a chip, which is a pretty cool thing to be able to do. But to make it work, you have to build a structure which has very, very sharp changes in composition over very short distances, and everything has to be just the right thickness so that the energy landscape that the electrons you inject see oscillates in just the correct way, and it causes it to emit coherent light. Neat. And once again, we had the case where somebody made one of these and the light it emitted was the wrong color. And once again, we put it in the TEM and it looks okay. See all the little atomic planes in it, they look about as they should. There's no discontinuities, no dislocations, whatever. But we throw the atom probe at it, and we look real close in, and we can see all these periods they tried to grow with different elements. And you notice anything different about one edge of this red stripe versus the other? Yeah, one side's all sort of raggedy. We got red atoms trailing upward from each one of these red stripes. Now these are gallium atoms. This is indium aluminum gallium arsenide. And the idea is they started at the bottom of this stack and they grew upward. And they turned on and off the little nozzles that squirt one atom or another. At least they tried to, but it turns out the gallium nozzle got stuck open. And it kept on flowing gallium longer than it should. And so every one of these, what are supposed to be sort of razor sharp little transitions, has a little tail of gallium, which changes the composition of the material above it and changes the energy landscape and makes this thing emit way out in the infrared instead of in the visible. But we're only talking a few atoms. I mean, you can see there, you know, what, a couple dozen gallium atoms. That's the kind of scale of composition measurement you need to be able to do in order to engineer a functional device like this. There's no other technique that I'm aware of that I can actually see things like this. Atom probe. Cool. What else can we do? Well, we can, of course, mix and match. If we have multiple different microscopy methods, and again, I'm not going to worry about what kind of microscope this is, and we want to target specific features, we can do things first in one microscope and then in the atom probe. We cannot do it first in the atom probe and then in some other microscope because the atom probe destroyed it, so it's gone now. But if we start in the TEM, we take piece of material, make needle out of it, see all these little structures, do our diffraction work, do our crystallography work, figure out what it all means, and then take it apart and figure out what its composition was before we destroyed it. And you can do that with other techniques as well, like diffraction mapping and so on, and it's all pretty cool. These are not easy experiments at all. These are very tedious experiments. Trying to go back and forth between multiple different instruments with the same incredibly delicate little piece of material is a long day's work, but you can do it if you really need to. Fine. What else do we analyze with atom probe? Literally anything. And I mean anything. I've done Belgian chocolate. I don't care what you've got. As long as it's not wet or porous, we will try it in the atom probe. Fine. Here's a meteorite. This is one of these Allende meteorites. It's called a CAI, calcium aluminum inclusion. There's little chunks of planetesimal bodies that used to exist way, way the hell back at the beginning of the solar system. Sure, why not? You want to know what those used to be made of? Fine. Give me a piece of it. We'll tear it apart in the atom probe. We'll tell you what all the atoms in it were. No problem. Even though it's really small. You know, the actual piece that they cared about was, where's my component on? It was right here, and this scale is, that's in hundreds of nanometers, so this is maybe a couple dozen nanometers high. Talking hundreds of thousands or millions of atoms. No problem. Atom probe will do it. This thing I showed you before, these are germanium nanowires grown inside of a 3-5. Again, very hard to do analysis on this. And depending on your growth conditions, you get different shapes, you get different diameters, you get odd effects where the wires start to sort of grow into each other and merge. There's a purely 3D system with all sorts of cool synergistic effects, but you got no way to analyze it other than atom probe. Works fine. How about a piece of the moon? Here's some Apollo 15 samples. These are lunar glass beads. They've been sealed up since the 1970s. They're still in our glove box because we're not letting them see air because they've never seen air from the moon. What's this stuff made out of? It turns out that on the surface of these little glass beads, which come from early lunar volcanoes, there are all these little metal particulates, which are teeny little meteorites that crashed into them over the 4 billion years they've been sitting there. And growing down into the volcanic glass are little branch structures. And what the heck's all that? Well, you can put it in TEM and you can get some sort of structural information. They're crystalline, which is interesting. There's glass all around them. But what are they made of? They're made of a titanium-rich crystalline structure called ilmenite. Catalysts, real popular stuff to do analysis on. These tend to be a bit of a pain because they tend to be porous. We have some ways around that. Sometimes it works. So here's some copper nickel catalytic nanoparticle aggregate. It's supposed to be copper nickel, but it was only supposed to be 0.01 nickel, so 1% nickel at most. And these nanoparticles are real small. They're order of 10 nanometers around, which means they only contain a few thousand atoms, of which maybe 10 to 100 are supposed to be nickel. It's real hard to actually work out if any individual nanoparticle has any nickel in it. Just, depending on the size of the statistical distribution, there might be some with none. Fine, so we pull out a piece, we do atom probe, we go look. Oops, skip it. Is that not a functional movie? It is a functional movie, it's just not set to play, whatever. Here are individual copper nanoparticles. You can see the boundaries between them. I've displayed copper and copper oxide. I have not displayed nickel because there wasn't any. Turns out that when they made these, they made copper nanoparticles and an occasional nickel nanoparticle. And then when they did composition analysis, they dissolve them all in acid and send them off for mass spec that way, and it came out at 1% nickel, but it's 1 nickel nanoparticle for every 100 copper. There's no actual nickel atoms in these copper particles. So now we know that. Oh, air-free, biological, hydrated, etc. Yes, in theory, you could do this. There are people trying to look at biologicals or battery materials or other things like that. Some of them are relatively straightforward to try and do. All of the ones with frozen water in them are very much not straightforward to try and do. We have other tools that can look at those kinds of materials. We do really good work on those kinds of materials. We're not doing ice samples and atom probe yet. However, if you really want to do that, I know the people who are doing it at MPIE, and I can send you about it. No worries. Okay, so summary of all the atom probe stuff. It is three-dimensional, volumetric, single atom time of flight. In other words, here's all your atoms and what they all were in a small volume. Data sets can be really big, billions of atoms. You don't need to. Don't try to go much bigger than billions of atoms because your computer will die. And we get part per million kind of sensitivity of everything. Caveat, hydrogen. Yes, we can detect hydrogen. The trouble is our atom probe is made of steel, and steel is actually porous to hydrogen. Hydrogen just runs right through steel like it wasn't there, slowly, but it does. So there's always some hydrogen background, which means our detection sensitivity for hydrogen is more like parts per 100,000 or worse. Not great. There are ways around that. If you think you've got hydrogen in your sample, you want to see it, just fill your sample full of deuterium, because there's not a lot of that out in the world. And again, we can tell the difference. So no problem. You can buy deuterium. If you can fill your sample with tritium, that's even better, but don't bring it to me. I don't want tritium. You got to choose, as with all microscopies, you got to choose your material and your sample carefully before you try and do these kinds of techniques, because these techniques are hard. And if your sample is not well matched to the technique, it doesn't matter how good you are with the microscope or the fib or anything else, you're not going to get a data set, and it's going to be very sad. But we can help with that. I can help with that. That's what we're here for. We can do your bulk compositions, your interfaces, grain boundaries. Basically, we can answer your composition questions over short distances with the atom probe. And if you've got a sample that we don't already know how to do, we'll try and figure out how to do it. We've done a fair number of these over the years. Wow, okay, so we've reached the end of this Franken talk, in which we mashed several different techniques. I'm happy to take any questions.